So first, the dissolving process. So in a solution, we have a solute which is dissolved into a solvent. And so to make the solution, the solute must be dissolved into the solvent. This is the process we call solvation. In a sense, if we have salt, we've got a little chunk of salt here, is that the molecules, NaCl, that are together here. Remember, we have our little water molecules. They're polar. They'll come in, and the positive side of that will grab the negative chlorine ion, and the negative side of the water molecule grab the positive sodium ion. And so then they'll take them off and spread them out throughout the material to create this homogeneous solution, because that's what solutions are. So it has to basically, the water molecules come in, take individual ions, pull them off, or take molecules in the case of something that is, if you're dissolving something that isn't polar or isn't ionic, and spread them out. So this sort of solvation process has to happen. It has to basically take apart your solute in order to make a solution. Now, let's suppose we want to speed up this process. You have, say, I'm from Alabama, so I like making sweet tea. And so to make sweet tea, you have to dissolve a lot of sugar into the tea. And so that takes a long time sometimes. If I want to speed it up, there are 3 things that I can do to do that. The first thing you can do to increase the rate of solvation is to increase the surface area of the solute. And so if you increase the surface area of the solute, that is going to basically give you a faster rate of solvation. And so an example of this sort of makes sense, because so in this case, the more sugar molecules the water can get to, then the easier it is to take them off. It's sort of like saying this, is that, if you have to unpack books, is that if they're all in one giant box, it takes longer to do it than if they're all spread out into a bunch of little boxes, especially if you have a bunch of people that are helping, or if you have a bunch of people helping. If they're all in one box and there are a bunch of people helping, there's only one person who can get to the box at a time. And so as a result, it takes a lot longer. If they're all in little boxes, everyone can go to their own box, take things out. The same thing sort of happens in this case, is that the more different solute molecules that are available to the solvent molecules, that is, the more that surface that's available, then the faster it's going to be able to dissolve it. Basically, if you have a large chunk of something, you try to dissolve that, it's going to take a long time. So what do? You typically, if you want to dissolve something, if you have a large piece of it, you crush it up. By crushing it up is that basically you're making the particles smaller, and so giving more surface area, the water molecules can get to each little individual bit of your solute a lot faster. And so this is the first factor that will increase the rate of solvation, surface area of the solute. The second thing, which affects how quickly a solution can be dissolved, the rate of solvation, is agitation. If you want to dissolve sugar into water, then if you just put the sugar into the water and you just leave it there, it will dissolve, but it will take a long time. What you're best off doing is basically stirring it. The more agitation you do, basically what you do is you make it easier for the molecules to spread out throughout the whole substance. If you just leave it sitting there, is that those solute molecules, the solute ions, will eventually make their way through the whole substance, but at first they have to sort of work their way there. By stirring it, you distribute them a lot more evenly, and so as a result, you have a faster, goes to solution faster. It dissolves the whatever solute you're dissolving much faster. The third thing we can do is we can change the temperature of the solvent. If I have a very hot solvent, then basically the molecules of the solvent are moving faster, and if they're moving faster, then one is that you'll be able to spread out your molecules of the solute a lot quicker through the whole substance. The second thing is it's more effective at actually pulling those molecules apart. The third thing, though, with changing the temperature of the solute, or so the solvent, increasing the temperature of the solvent, is that whenever you do that, is that you're basically giving more energy into the system. And by having more energy in the system is that you actually can hold more solute in your solution than you could before. And that's what sort of makes this third guy somewhat unique. And so this one right here is actually more important than the other two, because while this does increase the rate of solvation, the solvent temperature doesn't only affect the rate, but also it affects the amount of solute that can be dissolved. A hotter solution will hold more solute than a colder solution for most salts. Now Not everything. There are a couple exceptions to this, and we'll get to one in just a second. But for most substances, for most possible solutes, the hotter the solution, the more solute it can hold. If I have water that's 5 degrees Celsius and I try to mix salt into it, NaCl, I can't mix as much, I can't dissolve as much salt into that 5-degree solution as I could into a 90-degree solution. I'd be able to get more to dissolve. If I tried to mix the same amount of salt into a 5-degree solution as I can to a 90-degree solution, I'd basically be sitting there stirring, but nothing would happen. That the solution simply won't hold as much salt at 5 degrees as it does at 90 degrees. So for each temperature, a solvent or a solution has a maximum amount of solute that can be dissolved in it, and this amount is called saturation. When a solution is saturated, it holds as much solute as it possibly can at that temperature. If you try putting more, it doesn't do you any good. So this is what we have here. Let's take a little bit more look at this guy here. Saturated solutions, as we said, saturated solutions hold the maximum amount of solute that can be dissolved in that solution. Additional solute, and I do have this sort of in quotes here, because if you add any more, it's not going to dissolve. It's not really solute, is it? Additional solute will not dissolve. Technically, if you add more solute, some of it may actually dissolve. But here's what happens: is that, and this is sort of a little bit of an aside, is that when the solution is at saturation, that basically if you add any more potential solute to that solution, is that while some of that will dissolve, there's also some of the existing dissolved material that will then come together and fall out of solution, that will precipitate out of solution. And so basically the rate at which the solute is being dissolved is the same as the rate at which the solute is reforming into precipitate and sort of undissolving, coming back together and falling back down to the bottom here. And since those rates are balanced, they're in equilibrium, is that if you add any more solute, it doesn't do you any good. And so saturated solutions, they hold the maximum amount of solute you can get in. You can't put any more in it. And if you add more, it just won't dissolve there. So saturation point of a solvent changes with temperature, as we said. For most salts, we used them before, as the temperature increases, the saturation point increases. And typically, if we want to measure saturation point, it's generally measured in grams solute per 100 grams of solvent. For most of our solutions we'll have here, in fact for this class I believe it's all solutions we'll have here, our solvent is basically just going to be good old water. And so typically when we describe the saturation point or the saturation of a certain solution, we'd say it's the grams solute per 100 grams of water. And so let's take a look at how we do this. In order to find these saturation points, in order to find what the saturation is, we basically need a temperature solubility relationship, a temperature saturation relationship here. And so you have a colored sheet which should have this on it, and that's what we're basically going to show right here. Here is a picture of a temperature solubility chart. What this basically has is on the x-axis we have temperature in degrees Celsius. On the y-axis we have solubility in grams per 100 grams of water. And we have different curves for different materials. And so we have, sulfur dioxide down here, lithium sulfate here, sodium chloride, let me cross through it, potassium chloride, ammonium chloride, all the way up to calcium chloride up here. Different materials, and you can sort of see their curves. So for the sodium nitrate right here, here's the sodium nitrates curve going right here. Basically what this shows is these simply show that for certain temperatures, how much of that substance you can dissolve in 100 grams of water. So let's take a look at, say, lithium chloride. Lithium chloride at basically at 5 degrees. So 5 degrees is right down here. And so if we go 5 degrees up until we reach the lithium chloride curve. So lithium chloride's here. Its curve is the blue one that sort of goes along in here. So if we go from 5 degrees right here, we follow that up until we reach the curve. Then we follow it back over to the side. And so we can see that at 5 degrees, you can dissolve as much as about 72 or so, 72, 73 grams of lithium chloride in 100 grams of water. That's as much as you can do. You can't do any more. What if we went to 50 degrees? 50 degrees, right down here, we go up until we reach the curve. When we reach the curve, we're going to go back over this way. And so we see that, assuming my line's pretty straight here, that at 50 degrees, you could dissolve as much as 90 grams of lithium chloride in 100 grams of water. What about at 90 degrees? If the water is 90 degrees, we follow this up to here, and then go back over to the side and read what it says over here, we see that at 90 degrees that you can dissolve as much as about 120 grams of lithium chloride in 100 grams of water. That seems a little odd, but that's actually common for a lot of things, is that you actually can dissolve more solute than you have solution, than you have solvent. And in this case, this warm lithium chloride is one of them. Looking at this whole graph, you could sort of see that for pretty much all substances on here, that as the temperature increases going out this way, is the solubility increases, that the saturation point increases. And so that's why all the curves sort of tend to have a little bit of an upward slope going up here. There are two curves that probably should stand out to you. One of them is this sodium acetate up here that sort of has this nice curve that sort of curves upward and then has a kink in it before going out this way. We're not really going to worry too much about this kink here, but basically what it deals with is it deals with the fact that sodium acetate forms hydrates. Remember, we talked about these hydrates where basically the molecules surround water molecules and they sort of trap them inside. Is that as this dissolves, is that its tendency to make a hydrate, once the water heats up to a certain point, is this tendency to make a hydrate breaks down. And so it's acting like a hydrate before it reaches the temperature here, which looks like it's about 55, 60 degrees, somewhere in that neighborhood. And so closer to 60, I guess. My line's not very straight. After that, it sort of acts like a normal molecule, and so the curve looks a little more normal. It's a little flatter. It's not nearly as steep as it was before. And so that's the first one we have here. The second one is one that is a little more important, and that is our sulfur dioxide down here. Instead of going up, its curve comes down. It decreases. What that means is that we can not dissolve as much sulfur dioxide into a solution at 30 degrees as we can at 10 degrees. It works exactly backwards than what we expect. And the reason why that's true is because the sulfur dioxide is unique of other substances that are on this chart. And it's unique in that everything on here is a solid but sulfur dioxide. Sulfur dioxide is a gas. Gases, not just sulfur dioxide, but gases in general, almost always have solubility curves that go down as the temperature goes up. That the hotter the substance, the hotter the solution, the less gas as a solute you can mix into it. And if you think about it, this makes sense. Gases are generally moving pretty fast to start with. If you heat them up, they're going to be able to move faster. If they move faster, they can escape more easily. And if they escape, you're not fitting as much into your solution. This somewhat you'll see this is a little bit of common sense, because you know that, say, the most common case of having a gas dissolved into a liquid is in pop. In pop, you have carbon dioxide that's dissolved into in solution inside your pop. Typically, do you drink pop hot or cold? You drink it cold. The reason why is it can dissolve more at a cold temperature. It can dissolve a whole lot more carbon dioxide into that pop, and so it will typically be fizzier. If you take pop and you heat it up, take some pop, put it on your stove, heat it up. Put it back into something and let it cool down first. Drink it. It's going to be flat as anything. Simply at higher temperatures is that it simply doesn't hold very much. And that's true for pretty much most any gas here. So it's sort of common sense a little bit here that this works. This also is true for ocean waters. It typically is that cold water holds more dissolved oxygen, and so fish typically do a little bit better, or it can be a little more inefficient with their bringing the water through their gills if they have cold water than hot water. Is that cold water tends to be oxygen rich because oxygen is a gas. And at lower temperatures, you can dissolve more gases than you can at higher temperatures. Exactly the opposite as it is for most salts. And so this is an example of how our solubility curves work, is that you can, anytime you're given an example, you just look for whatever substance this is. And for this class, everything will be something that's on this chart. I'm not going to give you anything else. There are solubility curves for temperature solubility curves for other substances. These are not all of them, obviously, but these are just the ones we're going to sit with for this class. You can find other ones online if you really need to know one, but that's what we sort of got here. Continuing onward, we've talked about saturated solutions, but there are a couple other types that we need to deal with here. First one, a solution which has less solute dissolved than the solution can hold is called an unsaturated solution. So, if a solution has as much solute as it possibly can, it's saturated. But let's suppose it has less. Let's take a look back at our previous graph here. Let's take a look at our lithium chloride. We always like that guy right there. And so let's suppose that we have 100 grams of water, and we're going to mix some lithium chloride in it. And the 100 grams of water is at 50 degrees, and we mix 50 grams of lithium chloride in. And so 50 grams lithium chloride, 50 degrees. So here's my 50 degrees right here. Here's my 50 grams lithium chloride. It meets up right here. That's well below where the curve is right there. And so I could add more lithium chloride if I wanted to. I can add it all the way up until this point right here, up until, what is that? That's about 92, somewhere about 90 grams. And so if I add only 50 to it, there's still more I could add. This basically, in this case, is called an unsaturated solution. In terms of the overall sort of picture here, is that for the lithium chloride, is anything that falls sort of below the graph, below the curve, is considered to be unsaturated. And so down here, this whole region right down here, is that would all be unsaturated for lithium chloride. If I was dealing with say, this guy up here with this sodium nitrate, then it would be everything below this curve would be considered to be unsaturated. It depends on the exact substance you've got here. So that's unsaturated here. We said before is that the things that are along the curve, right dead on that, those are ones that are saturated. So that's saturated that's right along in there. Right along the line, which would leave everything that's above the line to be something else. If we're above the line, then basically we're in this region right up here. It's going to be something even different. It's things that are up in that region right there, which are generally not possible. Remember we said that typically you could only add as much solute up to the saturation point. There are circumstances, we'll talk about in just a second, where you actually can end up with a little bit more than your saturation point. And those solutions are called supersaturated. And I know this looks fairly confusing right here, but you sort of get the general idea, is if you've added less solute than the solution can hold, it's unsaturated. If you've added just as much as it can possibly hold, it is saturated. And if you've somehow tricked the solution into holding more than it's supposed to be able to hold, it's considered to be a supersaturated solution. And so some definitions sort of continuing on that would be, is in some cases, and here's the way that we basically get a supersaturated solution. If the solution is saturated to start with, and so we start off with a saturated solution, then what we do is we cool it very, very slowly. Remember that our general graphs on these typically go up like this. If we have one where we've got a saturated solution, it's at this temperature, it's right up there. If we cool it very slowly, then what can happen is that you end up with a solution that ends up right here. That it holds more stuff than what it should be able to hold. This, it says, holds more solute than the saturation point. This is called a supersaturated solution. Normally, whenever you cool things down, if you cool it down rapidly, or you cool it down rapidly and you shake it up a fair amount, or you disturb it in some way, then what will happen is whatever's in here will just precipitate out. This amount that's sort of the difference right in there will just fall out to the bottom. It forms a solid, and it'll fall out, assuming it was a solid, that your solute's a solid. If the solute was a gas, it would just release whenever this happens. But if you do it very, very carefully, and typically you have to cool it slowly and you have to keep the solution very, very still, don't put anything into the solution, and if you do that, then it'll basically hold more solute in the saturation point. It'll stay supersaturated. But if you take this solution and you give it a bump, then what can happen is everything, the difference in here, the part that we sort of showed right up in there, that difference there will fall out, and so it'll all drop to the bottom. It'll precipitate out. So a supersaturated solution, when disturbed, will quickly precipitate the excess solute and return back to the saturation point. First time you saw this slide, you noticed what was down in the bottom right corner. The classic experiment of you take a 2 liter or 3 liter of Diet Coke and you drop a Mentos into it. And you get this nice fountain effect that we see down here in the picture. The reason why this works is that carbon dioxide that is in pop is actually supersaturated. What they do is that they put the pop under pressure, and when they put it under pressure, they basically push all that carbon dioxide into it and they get it to dissolve. Is that then whenever you release the pressure, typically, you know, if you have a bottle of pop and you release it, is that you know what happens here. The carbon dioxide starts coming out. You'll start seeing bubbles start rising here. The reason why is that carbon dioxide is now precipitating out of solution. It was supersaturated, but you've now disturbed it. And so you've disturbed it, and so it starts coming out slowly here. So it's precipitating out so that it'll eventually reach its saturation point, which is basically flat pop. The particular chemistry of Diet Coke, though, means that if you drop something that has a very rough surface, and a Mentos turns out to have an extremely rough surface, and when I say rough, basically what I mean is that the roughness of the surface corresponds roughly to the type of things that carbon dioxide likes to attach to and form bubbles on. And so whenever you drop a Mentos into a Diet Coke, is that all of this carbon dioxide, which is above the saturation point, suddenly is disturbed, finds a spot for it to be able to grab onto and form bubbles, and all of a sudden almost all of that carbon dioxide, which was supersaturated, suddenly comes out of solution all at once, and guess what you've got? You've got this nice big boom, just flies out of here in every which direction like this. This is what happens whenever you have a supersaturated solution of a gas, and all of the gas, or almost all of the gas, comes out pretty much instantly, is you get this thing where it's like, boom, this comes out here. If I had, say, a solution of a solid, then basically you would see all the crystals fall out. It almost look like snow forming as they sort of fall out slowly, and they precipitate down to the bottom. It returns to the saturation, and it will go until it returns to the saturation point, whatever that is. And so this is unsaturated versus supersaturated solutions.